From knowledge bases, to ontologies. This is episode 4, Ontology versus its neighbors. Last time we walked 40 years of history, and watched the word ontology pick up company along the way: rule systems, semantic graphs, knowledge graphs, and now large language models. And here is the honest problem. In practice these terms get tangled together constantly, even by experienced engineers. So today we are going to draw some sharp, clean borders. By the end you will be able to tell each neighbor apart in a single sentence, and you will finally meet the one small equation I have been promising you since episode 1. Let me start by being honest about why this episode even exists. Of everything in this series, this is the single point where students get most reliably confused. Someone learns what an ontology is, and then immediately asks, but isn't that just a knowledge graph? Or, isn't that the same as a rule-based expert system? Or, can't a language model simply do all of this now? These are excellent questions, and every one of them deserves a crisp answer. So picture an ontology sitting in the middle, with 4 neighbors around it: rule systems, semantic graphs, knowledge graphs, and language models. One by one, we are going to walk the border with each. Our first neighbor is the production system, the classic rule-based engine of the old expert systems. The difference here is the deepest one in the whole episode, so do hold on to it. A production system is procedural. It is a pile of if-then rules that tell a machine how to do something, step by step. An ontology is declarative. It describes what is, the things in a domain and how they relate, without ever saying how to act on them. How to, versus what is. Think of it this way. The ontology is the engine, the formal structure of the knowledge itself. The rules are the fuel that drives one particular process across it. A rule, in the end, is just an axiom put to work. The second neighbor is the semantic graph, the kind of pretty bubbles and arrows diagram you have surely seen many times. Here the distinction is subtle, but it really matters. A semantic graph is a visualization, a picture, drawn for a human to look at and grasp quickly. An ontology is a formal specification, something precise and machine-readable, that a computer can actually reason over. Put it simply. The graph is the visualization of the ontology. The ontology is the schema behind the graph. One is for your eyes. The other is for the machine. They very often describe the exact same knowledge, but they live at completely different levels of formality, and you should never mistake one for the other. The third neighbor is the semantic web, and we will keep this one deliberately light, because it earns 2 whole episodes of its own very soon. The semantic web is the larger vision. Tim Berners-Lee's dream of a web of machine-readable meaning, and the W3C built a full stack of standards to make it real. The ontology's place inside that stack is precise. It is the cornerstone, expressed in the web ontology language, OWL. So an ontology is not a rival to the semantic web. It is one specific, load-bearing layer inside it. We will take that whole stack apart, piece by piece, across episodes 5 and 6. And now we arrive at the neighbor that causes the most confusion of them all, the knowledge graph. So let me hand you the one equation this entire episode is built around. A knowledge graph equals an ontology, plus data. That really is it. To say it just a little more formally, every knowledge graph has 2 parts. The T-box, the terminology, which is the ontology itself, the classes, the properties, the rules. And the A-box, the assertions, which is the actual instance data, the millions of specific facts. The ontology is the empty blueprint. The data fills it in. A knowledge graph is simply both of them, living together. Hold that equation in your head, because almost everything else clicks into place around it. Let us make that concrete, with a tiny example written in Turtle, a standard syntax for these triples. Down at the A-box, the data level, we might write, Jack Ma, founder of, Alibaba. And then, Alibaba, founded in, 1999, typed as a date. Those are raw assertions, individual facts about specific individuals. But notice what they quietly assume. They assume there exists a class of companies, and a class of people, and a property called founder of that links the two. That assumption, the classes and the properties, lives up in the T-box, the ontology. The A-box states the facts. The T-box defines what kinds of fact are even allowed in the first place. If you have ever touched a database, there is an analogy here that makes the whole thing snap into focus. The ontology is exactly like a database schema. It defines the tables, the columns, the types, the relationships, the shape that any valid data must take. And the knowledge graph is that schema, plus the actual rows, the populated database, full of real records. A schema with no data is just an empty design. Data with no schema is just a heap. You genuinely need both. So when someone asks whether an ontology and a knowledge graph are the same thing, you can now answer with precision. No, one is the schema, and the other is that schema brought to life with data. The fourth and final neighbor is the one everyone is talking about right now, the large language model. And this contrast is worth drawing across 5 clean dimensions. On storage, an ontology is symbolic and explicit, a language model is parametric, its knowledge smeared across billions of weights. On reasoning, an ontology follows formal logic you can trace, a model does pattern matching you cannot. On updating, you edit a single fact in an ontology, you must retrain or fine-tune a model. On semantics, an ontology's meaning is precise and defined, a model's is statistical and fuzzy. And on interpretability, an ontology can explain exactly why, a model is a black box. Explicit and verifiable on one side. Implicit and fluent on the other. But here is the twist that makes this episode hopeful, rather than combative. Ontologies and language models are not enemies at all, they are a near-perfect team. The pattern is called ontology-grounded retrieval, and it runs in 5 steps. First, you ask your question in plain language. Second, the model parses what you actually mean. Third, it maps that meaning onto the ontology and generates a precise query. Fourth, it retrieves the exact, verified facts. Fifth, it writes a fluent answer, and the ontology validates that answer against its own constraints, before it ever reaches you. In published studies, grounding this way lifts factual recall by over 50%, and answer correctness by around 40%. The model brings the fluency. The ontology brings the truth. There is one more neighbor worth naming, because it is brand new, and close to my own research, the LLM Wiki. Andrei Karpathy floated this idea quite recently, knowledge written in plain markdown, curated by and for language models. It is genuinely useful, and it sits at the opposite end of a spectrum from a formal ontology. An ontology is enterprise-grade, W3C standards, validation with shackle, and a real cost to build. An LLM wiki is personal-grade, no standard, no formal validation, but very nearly zero barrier to start. One buys you rigor and proof. The other buys you speed and reach. Neither is wrong. They are answers to genuinely different questions, and knowing which one you actually need is half the skill. So where is all of this heading? Toward fusion, in both directions at once. In one direction, language models help us build ontologies, drafting them straight from raw text, proposing the concepts and axioms we had missed. In the other direction, ontologies make our models trustworthy, grounding them, constraining them, giving them something solid to be checked against. This is exactly where my own work lies. I build what I call 4C verified knowledge, correct, consistent, current, and complete, using neurosymbolic checks, with tools like Z3 and Prolog enforcing the rules at runtime. The deployed agents in my lab run on precisely this pairing. The lesson is a simple one. The neural and the symbolic are far stronger together than either could ever be alone. Let us pull every neighbor we have met into a single map. Down at the bottom sits raw data and rules, procedural, specific, close to the machine. In the middle sits the ontology, declarative, formal, the schema of meaning itself. The knowledge graph is that ontology with its data poured in. The semantic web is the whole standardized stack it lives within. And the language model floats alongside, fluent but unverified, reaching for the ontology to anchor itself. Each one occupies a distinct, defensible place. None of them is simply a worse version of another. They are different tools, for different jobs, and the real skill, the one this whole episode is about, is knowing exactly which one a given problem is asking for. So there are your sharp borders. An ontology is declarative, not procedural. It is formal, not just a picture. It is a schema, not the data sitting on top of it. And it is explicit, where a language model is implicit. And the equation to carry away with you, the one I promised all the way back in episode 1, is the simplest of them all: a knowledge graph is an ontology, plus data. Next time, we stop talking around the standards and open them right up. Episode 5, the formal stack, RDF schema, and OWL, the three languages that turn all of this from an idea into something you can actually write down. See you there.